Before we begin with MD simulations, it is important to first decide which properties we want to study in our system. This step ensures we focus on right aspects of simulation. Thermodynamic properties are among the most common ones examined in MD simulations, regardless of the field. These properties include temperature, density, pressure, and heat capacity, particularly when the system is at equilibrium. It is crucial to note that these properties can only be accurately measured once the system has reached equilibrium. If we take the measurements before this, the values will differ significantly from what we would observe in a real experiment. For instance, imagine you are simulating the melting of ice into water. Let's say the system reaches equilibrium at 25 degrees Celsius. At equilibrium, if you measure the density of water, it would be 1 gram per cubic centimeter. However, if you measure the same density at 3 degrees Celsius, it will be lower because some of the ice will still be solid and only a part of it will have melted into water. As a result, density won't match that of the liquid water at 25 degrees Celsius. To ensure you get accurate measurements, your system must be in equilibrium. But how can we confirm if the system has reached equilibrium during simulation? A system at thermal equilibrium has stable energy values. Both kinetic and potential energies become constant. Before equilibrium is reached, these energies fluctuate, but once the system stabilizes, the energy values will level off. If you plot the kinetic energy against the number of empty cycles, you will notice a wavy line indicating that the system is still out of equilibrium. Once it flattens into a plateau, it shows that system is in a state of equilibrium. Generally, we study two types of properties in MD simulation: static equilibrium properties and dynamic equilibrium properties. Static equilibrium properties are those that remain constant over time. These include thermodynamic properties like temperature, pressure, and heat capacity. Other examples include entropy, Helmholtz free energy, and Gibbs free energy. The radial distribution function is another important static property that describes how particles are distributed within the system. For ideal gases, this function equals 1, but any deviation from this value indicates interaction between particles. Since radial distribution function doesn't change over time, it's considered a static property. On the other hand, dynamic equilibrium properties change over time, even when the system is at equilibrium. This might seem strange, as we expect equilibrium to mean stability, but certain properties, particularly those linked to the motion of atoms or molecules, experience very small fluctuations. These fluctuations are a part of what we call the dynamic equilibrium. An example of dynamic property is a diffusion. Consider diffusion of ink in water. When you drop ink into water, the ink particles, which are more concentrated at the point of contact, naturally move towards the areas of lower concentration. This process continues until the ink is evenly spread throughout the water. Even after the ink appears uniformly distributed, the particles are still in motion. They form temporary concentration zones where ink particles cluster together. They then disperse again to achieve the uniform distribution. This constant motion and fluctuation is what makes diffusion a dynamic equilibrium property. Beyond these general properties, MD simulations are also used to study specific properties of biomolecules, such as proteins in the field of biotechnology. For example, in year 1975, a pioneering study used MD simulation to investigate a protease enzyme called protein trypsin inhibitor. This enzyme is a serine threonine protease dissolved in a particular solvent, and the goal of this study was to understand how amino acid sequences influence the protein's 3D structure. Researchers wanted to know how distant amino acids interact with each other to form a protein's three-dimensional complex structure. To answer this, the authors simulated folding process of a completely denatured, which is unfolded protein, and tracked its folding in a solution. They then compared the simulated folded protein to the crystal structure of the same protein and calculated the root mean square deviation, which is RMSD, to determine if the simulated protein has folded into its stable or native conformation. The study revealed that short-range forces such as hydrogen bonds between nearby amino acids and hydrophobic interaction inside the protein play a role in a protein folding. However, the authors concluded that short-range forces alone couldn't fully explain the protein folding. Instead, they identified long-range forces, what they termed to be long-range effective forces, as the crucial for the folding process. This work conducted by Michael Levitt and Arieh Warshel at the Weizmann Institute of Science was groundbreaking. It contributed to our understanding of protein folding and earned them the Nobel Prize in Chemistry for combining the classical and quantum mechanics to predict the outcome of the chemical reactions. Their discoveries further paved the way for the development of anti-cancer drugs. MD simulations have also been used to study radiation's effect on metals. A 1960 study by Gibson, for example, focused on the impact of high energy radiations on the copper metal surfaces. In this study, thin copper plates, only a few atoms thick, were bombarded with high energy alpha particles at low temperatures. The researchers then observed how the copper plates recovered from the radiation induced damage. Although the damage was relatively simple, it showed complex characteristics that weren't fully explained by the existing theories. To address this, the author designed a model to study radiation damage to copper metal. Through their simulations, they predicted the damaged lattice structure that would result by applying the 400 electron volt of radiation to an atom in the lattice. They also investigated how energy from radiation would transfer to the neighboring atoms and how the moving atoms would lose kinetic energy. Additionally, they examined the stability and configuration of the atomic lattice. These are just a few of various properties that can be studied using MD simulation. In the next video, we will explore how to calculate the static and dynamic thermodynamic properties based on the position and velocities of molecules present within the system.